Hello, my name is BISTREANU and I would like to present you today some interesting AI applications based on acoustic signals. I will start with presenting you this classification of the signals we are going to talk about. Probably there are other ways to classify these, but this approach offers us a perspective of how various are actually the applications that surround us every day. Therefore, we are going to start with speech signals. Then we are going to dive a bit deeper into music applications, and finally a mini project that I consider the most interesting about bird sounds in the nature. Now, this is a diagram that contains some of the many applications that can be done with AI on audio inputs. Starting with our first subchapter, the speech. More exactly, I am going to present you the best models we have today for automatic speech recognition, developed by the well-known tech giants. As we can observe from this diagram, maybe not necessarily the best, but one that gathered the most attention from the public is Whisper, developed by OpenAI. Here we can have a look at its architecture. Keep in mind this detail here, the log-mel spectrogram, which I will talk about a bit later in this presentation. Now, my curiosity was how easy would it be to integrate this Whisper functionality into a React app. First reason that comes to mind would be for accessibility reasons, for people that might find themselves unable to type or click properly and could be helped by the possibility of having an audio input. And this project can also be found on my GitHub, and I also prepared a little demo for you. This is the demo of the application. The size of the model can be chosen from here, and also the desired language. The small size is one of the fastest. Madrid is the capital of Spain. Now when we press transcribe, in some time we should see what Whisper has understood. And here we have it. Madrid is the capital of Spain. For the other direction, text can be inserted here and then spoken, but I don't think this can work while recording. The next subchapter, music processing, can cover an abundance of applications. The generative part I covered together with my colleague Mai, in which we made use of GANs and diffusion models to generate visuals for song. But the other way around can be done as well, when music can either be generated out of prompts or visual cues. Recommendation systems of today also use AI quite often, such as Spotify and lately YouTube. For this part, I prepared a classifier that can accurately output the genre of a song. For this, I used the classical MLP, a type of deep neural network that is still considered today one of the best available classification tools. It's been proven mathematically that MLP, a multiperceptron with enough layers or neurons, can perform almost any classification task, depending of course on its difficulty and the data we have. For genre classification, I read that one of the best approaches is to feed the NN the spectrograms of the audio inputs, making it more of an image classification. Here we have examples of these spectrograms for some of the genres. Us, humans, might not be able to tell that much from these photos, but an AI trained well enough can gather all the necessary information out of this in order to accurately predict the respective genre. Are you curious how accurately? The accuracy I have obtained is 90.52%, only using classical MLP, whose architecture you can observe on this slide. And here we have the learning curves, which are more or less what an AI engineer would like to see at the end of his working day. The accuracy is increasing and the loss is decreasing. For the last subchapter, I prepared an application which I really enjoyed reading about and implementing. Before I present you the actual thing, I should make a brief introduction to sound event detection. It's a system that wants to recognize the sounds happening in a scene along with the length, start time and stop time of each individual sound. For example, in movies, it can be very useful for people that have auditive disadvantages to be prompt when the sound of something that fell happened, or when people are laughing, or when a door was shut. Same logic follows the second part of this slide about labeling. In the above example, we can see this type of recording that has all the events labeled and clearly segmented with stop and start times. Because this segmentation can be often expensive, tasks of sound event detection can also be carried out using weak labels, which means that we know the variety of sounds in the respective recording, as in the example laughing and whatever, but not the exact times they have started or stopped. Therefore, this is the problem I try to tackle, specialized on bird vocalizations. I found this dataset of bird songs in a Kaggle competition from 2020, and the task was to predict the start and stop values of each bird in given recordings. For this type of problem, the architecture of the system is a bit more complicated. For beginning, the input audio signal has to be quite heavily processed in order to obtain the log-mel spectrogram that I mentioned before. Well, these spectrograms offer so much value and information to PAN, which are actually a set of pre-trained audio neural networks. Also, this architecture makes use of a final attention-based pooling layer that has been modified to predict the 264 bird classes. Yes, 264 bird classes. For monitoring the performance of these systems, classical accuracy is not the most appropriate approach. Therefore, I chose to use F1, which highlights false positives and false negatives. For example, a false positive is if we say that there was a bird, but it actually wasn't. And false negative is that we say there was an old fly, a type of bird, for example, but actually there was. MAP, similarly as F1, considers both precision and recall, and it's useful when we output ranked probabilities, which in our case are the confidence levels of each prediction, in order to make sure that the model is learning and also becomes more confident in its answers. As for conclusions, we covered various AI architectures which highlight the importance of always doing our research beforehand and choose the appropriate model depending on the task at hand, as well as the metrics. As for the ethical part, many applications can be beneficial, either in terms of accessibility, content filtering, nature conservation, but also we should always pay attention when using sensitive data. This is the end. Thank you very much for your attention.